So let's figure out an expression for a thin uniform rod, the moment of inertia of thin uniform rod. So we have a case wherein we are considering a uniform thin rod of mass m, so entire mass m, length is L. It's rotating about an axis that is passing through the center O, and it's perpendicular. So the axis of rotation is perpendicular to the length. So as you can see, the axis of rotation is exactly at the center of the entire length. If this entire length is L, so this is at the center. So half the way will be L by 2 and the other half will be minus L by 2. Right? As per the coordinate, this will be minus L by 2. So this too, the funda is same. So we are making use of is equal to r square dm. Now to integrate this, what we have to do? We have to do a bit circle, get an expression for r, get an expression for dm, and you're done. So basically, for above integration, we can divide entire length to into many small parts of length dx and mass. Okay, length dx, that's enough. So we are dividing this into many parts, right? So after that, what should we do? So I have this small animation. So we are considering a small part dx. So from one end to other end, we just need to add them up. So that's the whole funda. So we'll start off with one small part, say over here. So that is my small part of length dx, which is x units away from the center. Which, okay, no. First is small parts of length dx. Next. So we will consider one such small part at x units away. So we have, therefore, our r will be x and dm will be equal to density times length. So our density will be the mass by, in this case we have a rod of length L, so m by L, and the length over here is dx. So on substituting into I, what we have is I is equal to, this is x square m by L dx, and we are integrating from one end, that is minus L by 2, to the other end L by 2. Right, that's what we saw over here as well. So from L by 2 minus L by 2 to plus L by 2. And now we have m by L is common. Then we have integration of x cube is, x square is x cube by 3. So minus L by 2 to plus L by 2. So a bit of math and you be end up with 3, and here we have L cube by 8 minus of minus plus L cube by 8. So we end up with, I'll write it here. We need the space. So L cube and all of that will get cancelled, 4, 12. So ml square by 12. Check the math. So we have 2, 4, 4 3 is a 12, L square. Okay, perfect. So that's the scenario. So we have ml square by 12. Now let's shift the rod to the extreme. Case, axis of rotation is at the end of the rod, perpendicular to its length. So what we have here is the same diagram, just that we have it over here. So let me draw this off. And we have this. That's our axis of rotation. And then we have this as a center through the center. We can call this as AB dash, A dash, B dash, and this is AB. That's what we are concentrating on. So we're trying to rotate this way, right? It's perpendicular to the length. So how can we do this? How can we figure it out? The inertia through AB will be inertia through A dash, B dash plus md square. This is as per parallel law of, sorry, not parallel law, parallel axis theorem. I was able to tell parallel law of vector addition, but it's parallel axis theorem. Okay, so this is, this we know. This is ml square by 12 and m is m. Here d will be what? It is L by 2 units away. And bit of math over here. So ml square is common. We have 1 by 12 plus 1 by 4. So 3 by 3, and this will be 4 and 1/3. So ml square by 3. That's your new value. So those are your two expressions related to this particular structure. Again, the funda does not change. Everywhere is the same thing. So when you are dealing with ring, you have to take up a small part dx and add it along the length. When you take up a disk, you take up a small ring of width dx and with radius x, and the radius will move from 0 to r. And then we have the rod, starts from one end, and we need to integrate it to other end. So that's the whole funda. So if we realize this, you are pretty much done with any kind of derivation if you get the funda.